Hi everyone, welcome back to my another tutorial. So this part will be about continuous proximal policy optimization tutorial with OpenAI GIM environment. In this tutorial, we'll learn more about continuous reinforcement learning agents and how to teach Bipedalwalker to walk. This is my example I chose from GIM environment and for learning purposes. And sorry that you had to wait so long for this tutorial because it's quite difficult code and it's quite hard to understand and code everything, so it takes time for me, so please respect that. And first of all, I should mention that this tutorial is continuation of my previous tutorial where I covered PPO with discrete actions. So this is something like one hot action. And if you missed it, you can find it on my website pylessons.com, and on the main page you might find this. And as you can see, here's the results, how my agent learned to land on rocket. So, to develop a continuous action space proximal policy optimization algorithm, first, we must understand that what is the difference between them, because, for example, this lunar lander environment has also a continuous environment called lunar lander continuous, V2. And I am mentioning that here is that there is two main difference between these two environments. So at first, discrete environment of this kind of landing ship actions. In this environment, there are four outputs: left engine, right main, and do nothing actions. And we send to environment which one we want to execute of these four actions. So in practice, we pick the action with the biggest value and send to the environment one number from 0 to 3. It means four actions. And in following environment, where is a continuous lunar lander, there is a box, some kind of box. This means that there are two continuous outputs where we need to send both outputs, and this will control the ship. The first output controls the main engine, and the second one controls left and right engines. The expected range of the output box is from -1 to 1 for both outputs. So we need to normalize the network to give us a values inside that range. So we usually do this by using tanh activation in my neural networks function. And well, actually there is the whole quote, and for more details you can read about that, and that's quite simple. I'm not going to explain this, but because this tutorial is not about lunar lander continuous. So we'll try to learn control different environment, and I'm talking about a Bipedalwalker robot. Following, we want it to learn to walk or run or whatever. It doesn't matter. It should move. I'll begin from 3 as always, and then we'll go back to the code. And here at the beginning I showed you the train model results, and of course I'll explain everything about it at the end of this tutorial. So reinforcement learning in the real world is still an ill-defined problem. Agent has to be greedy, but not too greedy actually, and one might conjecture that an optimal agent should have bayesian behavior, which again is not always what we want, nor the design goal of our brain. We want the agent to be curious so they could exploit the environment whenever possible, but not too curious so that they will continue to work for us. If you were the head of company, it could all be compared to training your employee. You want your employee to be exceptionally efficient at his job, while at the same time you want them to stay working for you, which is hard, if not impossible. Of course, unless you're a Google. That's a joke. And here's a Bipedalwalker environment, as you can see from this image, which is very hard environment in the GIM. Your agent should run very fast, should not trip himself off, should use as little energy as possible. And if you were checking the links I gave here on my websites, you may have noticed that it's V2, not V3. But in my code you'll see that I use a V3, and This is because Gym didn't update the link. After installing the V2 environment, it simply won't work after installing the Gym environment, because there was some kind of mistake in V2 environment, so legs were in some way crashing with each other, and our walker couldn't learn to walk properly. Anyway, if I go back to my walker, as you can see, it's quite hard to find online what does it mean solving environment, but what I should say, I found it, and I think it's here. Yeah, and it requires on average total rewards of over 100 consecutive episodes to be considered as finished. Well, which is incredibly difficult. Less than 10 people sold it on the Gym. Of course, I had somewhere the link for it, but I don't have it. I don't know. Leaderboard probably. I'm not sure if the results are legged. Here it is, Bipedalwalker. And as I said, I'm not sure if the results are legged and official, but I found them, as you can see. And in my implemented PPO agent on this tour can't break that 300 score mark, but at least I thought it can't. But simply while training my agent, the performance, well, actually this was at the beginning of developing. Well, I couldn't improve my agent to get better scores, but I don't know what was exactly the issue, but I found it and I fixed it, and right now I am able to solve this environment according to the following rules. But there is usually that my agent does stupid mistakes and falls, and this repeats time to time, and I'm not sure how to solve this, but that's quite fine for me. So talking further, there are a lot of information about these Bipedalwalkers, and because this is quite old games from 2017 or 18, I'm not sure exactly, but there is people who sold, and officially and not officially, but well, it's not that easy to find the codes they use. And of course, if you find a code, it's not that simple to reuse that code. So I thought that, okay, I'll try to write code in a way that everyone could reuse and understand. Maybe that's not a proximal policy optimization in 100% as written in proximal policy optimization paper, but at least I'm close to it, and I hope to hit the same results quite soon. So usually when we are programming a standard reinforcement learning agent, we don't care what is the observation space. Our agent should fit to whatever it is, but it's better to know what are the inputs in case if our agent is not learning. So here is the observation table from following link. The same link. There are 24 different parameters in one state. As you can see, there's a lot of joins, and if you notice my image, you can see that there is a terrain and there is nothing similar to it. So our agent don't know what is that terrain, what is the environment he's running in, and whatever. He has a LiDAR and he could use it to find the environment differences, but it's another topic for this, and it's much harder topic because about this hard environment. Next is there is a 4 action space. Each leg has 2 joints, and you have to teach the Bipedalwalker to walk by applying the torque on these joints, 4 joints. You can apply the torque in a range of -1 to 1, shown in following table. Agent gets a positive reward proportional to the distance walked on the terrain. It can get a total of more than 300. I couldn't get more than 330, I think, and all the way up to the end. If the agent tumbles, it gets a negative reward of 100. And there is some negative reward proportional to the torque applied on the joint, so that agent learns to walk smoothly with minimal torque. Also, I must mention that there are two versions of the bipedal environment based on the terrain type. So as you can see, here is a hard one, terrain, and I will try to teach this agent on a easier one, and this was this one, a slightly uneven terrain where there is no objects we don't see and we won't crash with them. So next, there are 4 walking strategies I should mention. Usually our agent tries all of them during the training process. And as you can see, there are 4 where you have a knee balance, double balance. This is the hardest but fastest runner. And front balance, there is a biggest risk to crash because you can fall forward. And there is a rear balance. And of course, there is also a big risk. So the best are this is the safest because we move but not so fast, and here is a double balance. It's the hardest to balance, but we move really fast. We can run as in our real life. We use 2 legs for that. So same as in my previous tutorial, first before moving ahead, I'll implement a random action agent interacting with this environment, and I will do this by have it here on the gist. And as you can see, I have Bipedalwalker random.py. And okay, I'll just copy this. Here's my whole stuff for this tutorial. And I'll just give it a different name. Py shouldn't be like that. And of course, I'll just copy this code here. So that's it. And of course, if I would run this, we might see that there's a lot of runners. Well, actually, there's a random, so this is why it's crashing so much, and it's not your problem. It's simply a random agent environment. So, okay, I'll simply shut it down. Doesn't care right now. So in this code, there's an action where we have an action, and we pick a random between -1 and 1 for an action, simply. And this is simply generated with a numpy. And I haven't printed here, but do we need this? I think we don't. So let's move forward. Now, you should understand why this environment is called continuous. There might be thousands of values. Well, actually, okay, I'll print this. Action, print action. As you can see. And it's quite hard to see everything, numbers, but there might be 1,000 of values between -1 and 1, where the actor should decide what action is best. These numbers control our robot legs. It doesn't make a lot of sense for us, but for our agent, it will do. Now, we successfully ran Bipedalwalker random environment, and now we can implement our PPO algorithm for continuous action space. So I'll shut it down, and we can move forward to our next step. The same way as the discrete proximal policy environment, continuous also uses the Electrocritical approach for the agent. This means that it uses 2 models, one called the actor and the other called the critic. And the actor model performs the task of learning what action to take on a particular observed state of the environment. And in the Bipedalwalker case, it takes 24 values list mentioned before of the game as input, which represents the current state of our walker, and gives particular actions what legs to move, as you can see. And this is represented in 10H probabilities of our model. So if we would look at our model, I have an actor defined here. And if we would compare our current actor in its custom continuous loss function with the discrete proximal policy optimization actor model, we would see 2 main differences. In the discrete proximal policy environment, and here's my output, our model had a softmax actuation within output in the last layer, and here we have a 10H, as I said. in continuous PPO and network, we use 10H instead. And also, we can remove the activation function at all, but then we don't know what output our model gonna learn to give us. It might give us actions outside of our action space limits. And the main difference is the custom PPO loss function, which is really hard to explain. And moreover, it's hard to understand, but of course, I will try. Why not? So, continuous proximal policy optimization loss action space defines the distribution used for action selection. The distribution is used to sample or select the action based on the specific distribution. And for a given action, the distribution defines its probability. This probability is plugged into the following formula, and actually the distribution usually gives us the log prob, and we plug it into the loss using exponential function. So it's the same formula in both cases, discrete and continuous. Just the distribution defines the action selection and its probability. For discrete action space, we have n linear outputs and a categorical distribution. In example, the outputs are the logits that defines the probabilities using softmax, and we sample based on those. In discrete actions space case, the probability is just the softmax value of the chosen action. Continuous action space use normal or Gaussian distribution. In this case, the model output is the mean plus standard deviation, which defines the normal distribution to use for the action selection. The action is sampled from the distribution. The probability is, in the case, the probability of the action's value under the given normal distribution. Well, actually, I don't understand all the math behind this, or I'm not sure if I understand, so I decided not to try explaining it and mislead you into a bad direction while understanding it. Also, I borrowed the idea of how to implement the Gaussian likelihood function into my code from Stable Bayesian's GitHub page, where I have it. Here is Gaussian likelihood function, and if you would analyze my code, here it is, you can see it. It's a little different because I have a log std here inside, but that's the way I found to implement it. And I couldn't understand and find out how to implement the log std parameter into my TensorFlow 2 code, so I used a simpler version of it as a constant parameter. If you have an idea how to implement log std, I'm open to you, up to your suggestions. Maybe in the future I'll find a better way. I'm sure that this parameter is responsible for continuous action space randomness. I'll show you this to you later, actually. Doesn't matter right now. The main role of the critic in continuous action space doesn't change from discrete. Model is learning to evaluate if the action taken by the actor led our environment to be in a better state or not, and give its feedback to the actor. Same as before, we send the action predicted by the actor to our environment and observe what happens in the game. If something positive happens as a result of our action, the environment sends back a positive response in the form of reward, and vice versa if we receive a negative reward. These rewards are taken in by training our critic model, the same as in my discrete environment, actually. So, when we are going from discrete action space to continuous space, we must change the code part where we are choosing an action. And here is the code where I choose these actions, actually. Act function, act continuous, I'm not sure how I could call it, but it is as it is. And first you should read the code to make sense what is the difference between my discrete and continuous action space. Okay, I'll open my environment. I'll give you a simple example. For example, if I have some kind of value, and it might be an array of predicted values. I'll create a few of them. And for example, it's 005, 085, and 0.1. Oh yeah, import numpy snp. And here's our predicted values, for example. And our action size is equal for 3. And what happens if I'll choose to do, for example, action equal to numpy random choice of a, and where p equal to predicted value. Yeah, a should be equal to 012. And now let's see what is our action. As you can see, our action is 0. But this is only, as you can see, here is the values, random values, and this for example value has the biggest probability to be chosen, and this is how it works in discrete action space. Well, there is some kind of randomness with weights of choosing, for example, one of them. So in this case, well, there was this rare action when random chose this, but usually it would choose this because this has the biggest chance to be chosen. So this is how it works in the discrete. And right now I can write a continuous action space example. For example, if our std equal to 0.3, we have, for example, some kind of random numbers. There might be 0.5 minus 0.7, 0.1, and 0.9. And we have some kind of predicted values. I'm not sure. I'll copy this. So we have random uniform and predicted values. So our action will be equal to predicted values plus random uniform multiplied by std. Yeah, I can't. This is how it should look. And you might see right now what is the real action with what is, for example, this is a predicted action. This is our generated random action with 0.3 weights, and this is our final action, which will do and this means that we will do predicted action with some kind of randomness. And this is how it's got. So we have covered most of the difference from discrete action space. We can finally start the model training. For this, I use mostly known the fit function, and it's written is in fully keras. Well, actually, this is the biggest difference and hardest thing is to implement proximal policy optimization, because it has quite hard to understand loss function, and it's very difficult to implement it in TensorFlow too. So I'll try later to get more knowledge in creating custom loss functions in keras so that I could fix mistakes I have in my code, because right now I have mistakes and I'm not sure how to fix them, because there is some code parts where there is really a lot of stuff where we can optimize everything, but I just don't know how to do this in keras. That's it. And from this code you can see that everything is quite the same, except instead of collecting predictions as we did in discrete action space, right now we collect log t's here it is. We stack advantages, actions, and log these to a numpy array, and we send these stacked variables to our custom PPO loss function while calling a fit function. After a fit function, you can see a little more code, but this is only for graph to track our model training performance. So if we would remove this, it doesn't change anything in our performance. Well, actually, it might work a little faster because we do a few more predictions here. So to glue everything to one simple and working code, it took me a few weeks, which is a lot of experiments. But right now, I can proudly announce that to train Bipedalwalker with it is not that hard task as it looked for me in the first days. My code took only, I don't know how many steps here, where it is. So my code took only 5,000 training steps to achieve maximum results, where 50 episodes moving average score was, I don't know, close to here is, it's 300 in between 50 and 20,000 steps, and running it on test environment was even better, as you can see. I haven't run it yet, but I can run it. For example, let's go to the end. Yeah, it's test. I can run, and you'll see that it's quite interesting how it learned to walk. Well, actually, as you can see, it sometimes crashes, but I can't do anything with it. So here it is, 330 and so on, and that's quite cool. And as we can see from this chart I showed you, the hardest task was to learn that we need to move forward somehow. This took around 1,000 or a little more training steps. When our agent understood that he needs to move forward as fast as possible, he started learning the walking strategies I mentioned before. After around 4,000 training steps, our agent was able to get around a maximum 300 score here. And as we can see, the 50 moving average is near 300, some here near, and here it hits it, and that's quite amazing. After training my agents, I decided to check if my agent can complete 100 episodes with an average score, and I'm not sure if it's saved right now. I don't have it here, but actually you can see that it works quite nicely. And here is my scores, and it usually hits 330. So yeah, I can hit the 300 score but in this average, and that's quite cool. So that's it. For a quite long time, I was unable to understand the difference between discrete and continuous action space in PPO, and this Bipedalwalker tutorial motivated me to get better understanding of how everything works and how I can implement everything from scratch. And by the way, gym environments are a great place to test how our algorithms implementations work. Without gym, I think it wouldn't be so easy. And this continuous environment still has a few places where I can improve it, but depending on the results I obtain it, I'm real proud to give you my working code, and I would appreciate your suggestions how I could implement Gaussian likelihood correctly. But anyway, even without your suggestions, I will try to do it in my spare time in the future. And anyway, I learned a lot while writing this tutorial, and I think in the future, while working on the other projects, I'm sure I will do them based on the code. There is still Bipedalwalker Hardcore V3 environment that I couldn't finish, so maybe I'll play around with it before moving to the next projects. So anyway, I hope this tutorial will give you some kind of understanding of the continuous PPO model and how to implement it. Do not hesitate to clone my GitHub repository and test it by yourself. So See you in the next part. Thank you all for watching. Wish me luck and thank you for watching. I wish you have a good and nice, clean lines of code in your coding, and don't hesitate to comment this video. Whatever you want, just comment it, write me, and you can fix my code if there is some mistakes you can see, and whatever, doesn't matter. So thank you all for watching. Goodbye, and see you in the next part. Goodbye.